Well, hello everyone. Thank you for coming and joining. Also, people joining us on Zoom. So the Distinguished Lecturer Series is our main event here at the Max Planck Institute for the Science of Light, bringing to you the thought leaders internationally in the science of light. Now, it's a particular pleasure to introduce today's speaker, Mercedeh Khajavikhan from USC in Los Angeles. Let me briefly introduce her. So she is currently a professor at the Electrical and Computer Engineering Department at the University of Southern California in Los Angeles with a joint appointment at the Department of Physics and Astronomy. She actually started out by doing her Ph.D. in electrical engineering at the University of Minnesota back in 2009. And then she moved as a postdoc to the University of California in San Diego. Afterwards, in 2012, she started her assistant professorship at CREOL in the University of Central Florida, and in 2019, she moved to her current position at USC. She has worked on a broad spectrum of topics in optics in general, like nanolasers, plasmonics, silicon photonics, and active photonic systems. And she's particularly well known for her works on the fields of topological photonics, PT symmetry, and more recently, optical thermodynamics. And just to mention two highlights, these are her path-breaking publications in PT-symmetric microring lasers and enhanced sensitivity at higher order exceptional points. She has won all the early career awards, basically, that there are from NSF, ONR, and DARPA. She has won a UCF Luminary Award and a DARPA Director's Fellowship, and she's a fellow of Optica. And today she will tell us something about guiding Trojan beams via Lagrange points. Very interesting sounding topic, and I think we are all looking forward very much to your talk. Thank you for coming.
Thanks for the introduction, and I'm really honored to be here. So the topic of my talk today is guiding Trojan beams via Lagrange points, and as Florian said, I'm Mercedeh Khajavikhan, and I'm from USC. Before I start, I would like to give you a little bit of a background about myself and my research. So as you heard, I did my PhD in University of Minnesota under the guidance of Professor James Ledger, and I worked on coherent beam combining for high-power laser applications. Then I moved to San Diego, UC San Diego, and with the change of the weather, I also decided to move to the other side of the spectrum and worked on very, very tiny lasers. So we showed the first threshold-less laser back in 2012. And this is a topic that I still, on nanolasers, is something that I still work on it in different settings. A few years back, we showed how this laser can be used to actually implement spin systems like XY Hamiltonians. And we even have ways to actually use them to implement I-sync Hamiltonians. Then I moved as a junior faculty to University of Florida, College of Optics and Photonics, also known as CREOL. And again, I changed the direction. I came to work on microring lasers a lot. And it was at the time that these ideas of PT symmetry and non-Hermitian optics has been actually started to gain some traction. So we first showed some, we can use these exceptional points that appear in these systems for laser mode management, something that I did as a PhD student and partly as a postdoc. We also, different type of symmetries we explored besides the PT symmetry. We looked at supersymmetric structures. And again, we used them in the context of lasers for, again, showing laser phase locking in arrays. And also, again, I worked on topological photonics and topological lasers. At the time, we showed the first topological insulator laser. We eventually showed it also optically pumped, electrically pumped. And one of the slides that you can see here, it's an effort to actually show for the first time the Haldane lattice in optics. So Haldane lattice is the lattice that you can actually, it was a toy model proposed by Haldane back in 1988. And where he showed that in certain types of lattice with different, with these hoppings, you would be able to get, without an external magnetic field, you still would get a topological state. And And I always say this looks like a Persian carpet, and in fact, it's a big structure. This is just a unit cell of the structure. But we fabricated this structure. This shows a very interesting way of implementing non-reciprocal next nearest neighbor coupling in an array. And then what I do these days is we got a grant to show some of the applications of novel topological materials. In particular, this is on the wild semi-metals, and we are using them now to actually, we have a way to make the very compact broadband polarimeters based on them. And as also mentioned, I work a little bit on the optical thermodynamics. It's a very recent field, basically studies what happens in highly multimodal and nonlinear systems. And instead of using the standard way of nonlinear Schrödinger equation or electrodynamic equations to solve this system and understand the light evolution in this system, it looks at it based through a statistical physics approach. So again, in this context, we are now looking at, we just recently, maybe last year, we showed for the first time negative temperatures in this system. We are also, right now, as we speak, we are working on how we can actually use these systems and the knowledge that we gather through this optical thermodynamics to implement new ways of coherently combining incoherent beams. So this is actually a very important and interesting problem. Again, going back to what I did as a PhD student in some ways. So I'm not going to talk about this topic, but today I'm going to talk about another recent work in my group that's very interesting. I found it very counterintuitive and interesting, and I like to talk about it. And I'm very excited to talk about it. And it's about Lagrange waveguides for light and charged particles. So starting from the guiding, of course, guiding of light is perhaps the most technologically important property of light, because it allows all this communication that you see, which undoubtedly change the way that we live. And there are many ways to guide light, but the most prominent way is, of course, using the total internal reflection, where we have a high index material surrounded by low index material. And through total internal reflection, we can in fact guide light. And guiding light, what we mean is just not the transporting of light, but also the fact that these guided modes are lossless way of propagating them, theoretically. Of course, we always eventually go to material system, there are some losses, but a guided mode absolutely, theoretically, doesn't have any loss. And guiding actually can happen in other systems as well. Most notably, if you have a periodic structure, there are many ways you can actually use this periodic structure to guide light. There has been a lot of work on surface plasma and polaritons and guiding through that. Gain guiding used to be actually used as an approach for making lasers. It's not as effective as index guiding, so it has been dropped by many. Coupled resonator optical waveguides, another approach for guiding lights, and BICs or bound states in continuum, and the list actually goes on and on. However, if we ask ourselves, beyond the total internal reflection, in fully dielectric and passive material systems, do we have a way of guiding light? It's not very clear that we can do it besides total internal reflection. So this brings us to the topic that I want to talk about today, which is guiding Trojan light beams via Lagrange points. So effectively, in collaboration with Dimitri Christodoulidis' group and our students, Hao Kun, Yuan Fan, and our postdocs actually, Fan and Yorgos, for the first time, we showed that, in fact, you can guide light in a bulk medium without having any periodicity. And with that, let me just update you on the concept of Lagrange points in case if you forgot. So Lagrange points are, of course, named after one of the most prominent mathematicians and mathematical physicists of all time, Lagrange. And And it was actually the problem, the points and the problem actually has been first studied by his Ph.D. advisor, I would say, Euler. And this is a problem, is a three-body problem. In physics, it's a very known problem. If you have three massive bodies, how you're going to find for each of these bodies, how you're going to find the equilibrium point that you can put these things. This is a very difficult problem to approach analytically. However, a reduced version of this problem, known as reduced three-body system, has been considered by Lagrange and Euler, and then eventually Lagrange. And this is where you have two massive bodies, like, for example, in this case, you could see that we have Sun and, let's say, Earth or Jupiter, these two massive bodies. And then you have a little asteroid, and you want to find out that in this system, where this little asteroid will actually experience an equilibrium position, or that net force is going to be zero. And as I said, Euler looked at this problem, the first person that actually looked at the problem, and he found these 3 points, L1, L2, and L3, which is almost trivial points to find. And these are all on the line that connect Earth, for example, Earth and Sun. And if you remember a couple of years back when they put the James Webb telescope on an L2 point in order to look in the outer space. And these points are actually not stable points. So these are the points that, even though they are equilibrium, they are not, if an object is placed at these points, it needs a thruster. For example, a telescope that's placed on these points, it needs thrusters to always keep it at place. Otherwise, any perturbation will actually put them out of the orbit. And then, as I said, later on, Lagrange looked at this problem, and he found two non-trivial solutions to this problem. I mean, non-trivial, not very easy to guess at least. And these points are now, first of all, collectively, all of them are named after Lagrange. I mean, it's not fair, but I think Euler wouldn't care. And the ones that Lagrange found are basically these L4 and L5. They are 60 degrees away from the axis. And they're very, it's somewhere 60 degrees. It's a very special place, and it doesn't seem that anything should be actually trapped in these points. However, it does. And so for a while, I mean, it was no use to it, or I mean, nobody actually observed them or cared about them until when they actually started to, in the early 20th century, when the telescopes became more advanced, and they were able to actually look at the sky and see some of the asteroids around Jupiter. And then they noticed that these asteroids are somewhere in the middle of nowhere, and they appeared that they nicely orbit and everything, but it just didn't have any immediate physics to explain what's happening. And eventually they remembered these Lagrange points and realized that, oh, these are actually the Lagrange points that trap the asteroids. So they started to name them after the heroes of the Trojan Wars, and so they found a lot of them, and in both 60 and minus 60 degrees. And one side eventually named after the heroes, the Greek heroes, and the other side named after the Trojan heroes. And there's a few that ended up in different places, but in any event. Nevertheless, the one side is called the Greek camp, the other side is called Trojan camp, and because of Trojan Wars, they call them, overall, they call them Trojan asteroids. It's just a little bit of a history. And for some of you that didn't make that connection, USC's football team is also called Trojan, so it was a coincidence, I would say. All right, so just a little bit of a, look at the mathematics of it. So we have two massive bodies, M1 and M2. We have a small asteroid with a small mass of M. And actually, you can show that this mass ratio, if it's larger than 27 or something like that, you will have these dynamics that we are explaining. So you can actually go to a co-rotating frame or a stationary frame, and write the overall force that this object is actually, for example, in the co-rotating frame, is experiencing. So you have a gravitational force, you have Coriolis force, and you have centrifugal force. And once when these three forces are balanced, you would be able to get that equilibrium point. And as I said, you can find all these 5 points based on this recipe. And if you look at the potential associated with, so if you have the force, we know that the potential is just the gradient of the force. So if you look at the potential, it's what you see in the right side. And this is very interesting because L1, L2, and L3, those potentials are, you can almost guess that something would be trapped partially, at least in those places, because they're like, they are like a ball, right? I mean, the potential is lower. L4 and L5 is completely the opposite. They are like this. In the fact that the object is trapped there and it's stable there, unlike the other three that are like this and they are still not stable. In fact, they are not like that. They are saddle points. But in any event, those two are absolutely no way of guessing, if you look at just the potential, that anything would be trapped on those points. In fact, if I was allowed to guess by just looking at that, I would have guessed that it's an anti-trapping structure. It's like a reverse, it's like a heel. However, because of the fact that we are in a rotating frame, and it rotates, that basically there is a Coriolis force that every time that the object that you put on these points, for example, then this L4 point, try to escape, it brings it back. Try to escape, it's some sort of a dynamical stability. Okay, so this is basically, again, the potential. You could see that, as I said, you could see that L1, L2, and L3 are okay. I mean, there's some sort of a going down, so there is some trapping happens there. As I said, these are not stable points. However, L4 and L5, it's dynamical stability and dynamical trapping. So in some ways, you can think about it like a Sisyphean kind of manner. I mean, remember that Sisyphus basically was pushing the stone on top of a hill, and it was coming down, and it's pushing it up. So this pretty much, that's what's happening here. So how we get this idea and bring it to optics? We already know that there is a direct relationship between celestial mechanics and ray optics. And in fact, I just wrote in a couple of equations, a couple of lines. This is the ray equation. And so the second derivative of ray vector is associated with the gradient of the refractive index. And if we are in almost a paraxial approximation, S would be almost equal to Z. And now if you look at this is no different, not different from the equation of motion. Just in this case, the gradient of the delta n is going to be your optical, your potential. So this, you can see that with this transformation of Z equal to CT, this is basically the same type of equation. So whatever we had, the potential that we have in the, oh God. All right, so the potential that we had that you saw that it's of course in the UXY at any given time, I can show you that, but of course you remember that it's a rotating frame, it rotates, right? So in it basically, the potential is like this. So there is a T dependence. And if you want to go to the propagating domain for light, the T is equal to Z is equal to CT. So I didn't find any good picture, but you can imagine that you're basically going from an index potential that is twisted when you actually do in the Z domain, right? I mean, hopefully everybody sees that. All right, so this is what you get when you actually start to look at the problem from the wave perspective. So let's say we have the paraxial wave equation, and we have the refractive index profile that we just talked about. And this refractive index profile, let's say that it has XY profile, plus a z dependence. That is, as we said, it's basically the potential is rotating with the angular velocity of capital omega. So in this case, I can just get this equation and go to a co-rotating frame. And through this transformation that, for example, defined here for u and v, based on the, the co-rotating frame, so everything, both x and y are rotating with the angular velocity of omega, I will be able to remove the z dependence from that equation and bring it to an equation that looks very similar to what we normally see as a paraxial wave approximation. So this is it, and you can see that, here we wrote it as a, again, V is just optical potential. I can put delta n. And you can see that this equation now looks pretty much similar to what you expect from is in shape, is similar or isometric to the Schrödinger equation in the presence of a magnetic field. So it is the Coriolis force that, again, remember. And when you actually go from celestial mechanics to optics, you no longer need all the potentials and everything, two bodies and so on and so forth, because all of that becomes an effective index profile. You can design it and put it in any possible way that you like to put it. So it's not the only thing that actually you need is to have this helical structure, so you have the rotation, or effectively you need to have the Coriolis force in order to guide and trap light. So to give you an example, and this is the example that analytically we are looking at it, and there is a very good reason for it, because in the experiment we are also generating this potential. So just to look at it, let's say we have a refractive index profile that has a logarithmic distribution in the transverse plane. And let's have this logarithmic distribution completely anti-guiding. So instead of having a refractive index that is higher at the center, we have the refractive index highest at the edges, right? We are going to study this system in a cylinder, in the cylindrical coordinate. So when I say the refractive index is highest at at r equal to infinity, basically we have the highest refractive index. So if anything, you expect that you send light in the system, it would, change its direction towards the walls of the tube, for example. Yet, when we are actually having this helical refractive index profile, we would be able to trap light. This is what you see for the index profile in the stationary frame. So this is where we don't have any, you look at one plane of this entire Z, let's say at Z equal to Z naught. So, and you could see here in the simulation, there are two Lagrange points, and one of them is stable. LA is the stable one in here, and LB is not stable. It just happens that in this particular case, this one is. And if you look at the same thing in the co-rotating frame, now you can see that, in fact, LA, in the co-rotating frame, I have like a trapping potential, and that's what you see here. This is the simulation of the guided mode in this structure. So what you see here is the intensity profile of the fundamental guided mode of this structure. We have a lot of freedom to design these waveguides in terms of what would be how many modes are supported by them, and where it's happening, what is the how good is the stability. We have a lot of parameters that we can play, like the location of the index distribution, the index contrast, how fast it goes up by the time that it reaches the walls. We can also engineer the size of the pitch as well as the size of the radius of the pitch. So we have the radius of the helical structure. So we have a lot of parameters. The simulations are mostly done for the experiments that we did, which I will show in a couple of slides. But nevertheless, you can see that the structure supports a guided mode. It looks like very much like a Gaussian beam, and in fact, it has some astigmatism, as you may guess, because the structure goes like that. So at every plane that I look at it, it doesn't. The Gaussian that I get is not having X and Y equal, and that's not surprising. But what is actually surprising, and it's very different from other waveguides that we saw so far, is the phase profile. As you can see, the phase profile here, it does not follow what you expect from a Gaussian beam. It has some sort of an X shape, and this is very unique to this structure. And again, it shows the fact that you are rotating, and that's how the phase is coming up like that. The trajectory of the beam is also shown over here. The beam is basically it travels along a helical path as well. So it is very different. I mean, as soon as I say helical, people usually think about OAM. The OAM, remember, the phase is helical. Otherwise, the beam is just going forward. This is a straight line. This is now, the beam itself goes through a helical path, and it's in a guided fashion. So it's interesting. All right, so how did we actually generate it in the lab? These points, I said, I mean, in fact, a disclaimer, we can use a lot of different potentials, but we stick to this one just because our experiments is easier to be done in this, we did it this way, and it's a very easy, simple experiment. So we used the temperature distribution, and through the thermo-optic effect, we generated the refractive index profile that we wanted. We know that if we put a wire in a cylinder, and we keep the outside the cylinder, the outer wall of the cylinder or the tube at a particular temperature, and pass current through the wire, we would get a temperature distribution between the central wire and the walls of the tube. And this temperature distribution follows a logarithmic behavior. I remember, I'm not sure about you, but we did it as a problem in physics, elementary physics courses. So it's very simple to calculate. So then we pass the current, and you can show that this delta T, the temperature difference that you get between the central wire and the outer tube, is going to follow that equation that you see, which of course depends on the thermal conductivity, and as well as the amount of current that you're actually generating also depends on the electrical conductivity. All right, so as I said, we fill this tube with a material that has, it's PDMS, it has a negative thermo-optic coefficient, and so delta N follows delta T, the temperature, through this equation. And you can actually get now the distribution of the refractive index in this tube. And if you are at any, so we solve the problem for a wire that passes through the center of the tube, and you can show as long as the outer tube is actually much larger than the wire itself, you expect that when the wire is going through the helical path, it would be just the shift of R to R0 over here. That's Z-dependent, depending on where you are. So this is the refractive index profile that we talked about. As you can see, it has a transverse relation, and a Z-dependent Z-dependence. And this Z-dependence, as I said, follows the helical structure. So the experiments is this. Basically, these are the tubes that I talked to you about. So they are almost 29 centimeter, almost 30 centimeter. And well, I don't know how well you can see, but there is do you see them? It's hard for me to see. But there is a wire that goes through them. So we are basically, we are making a pre-form or form for the wire with the proper pitch. We're using a 3D printer. And then we put the wire around it with the proper pitch, and then take it out, put it inside the tube, and we fill the tube with the PDMS, which is also known as silicon gel, and then cure the PDMS, and basically that's the tube is ready for experiment. Next to the one with the one wire, you see also a structure with two wires. And I didn't show the mathematics of it, but with the two wire, you would be able to actually get light that propagates along a straight line as an interference of these two Lagrange points. So this is what you expect, what you see when you have a single wire. It's one of the early experiments, so the wire is not very clean. But nevertheless, what is important is that as you could see, because we have this defocusing index potential, when we excite it with the light from the left, you would be able to, the light basically deflects towards the wall of the tube and then reflects back and so on. So this is what you see from you expect in a system that you have a defocusing potential. Of course, if you have two wires, you get one of these points that are saddle points. So saddle points are focusing on one side and defocusing on the other side, like a saddle. And you can actually, again, you see that the light propagates and diffracts in them because there is no guiding, right? I mean, these structures are, none of them are favorable for guiding. Now, as I said, if you look at the structures when we actually have the wire with the proper pitch, and then we can excite it, and you can see that the light gets trapped and gets guided through this structure, and you can also see that it follows a helical trajectory. You can see that it is the size remains constant and doesn't grow. You can see that it is not diffracting. And this is the same, actually no, this is where we have the same structure, but we do not apply any current. So the current is equal to 0. And you can see that without applying any current, what happens is that the light diffracts because there is no guiding again. This is with the double wire when you have a double helix structure, and you can see that in these systems, when again, when you are applying the current, you would get and of course you have to excite the system at the right point because this guiding only happens in a certain point. You would see that you get guiding, and when there is no current applied, there is no guiding, and the light just goes through the material and diffracts. It's a material with a refractive index of 1.5-ish. So what is surprising here is the fact that we are actually guiding again. I mean, somewhere that you do not expect any type of trapping. It's like you see that all of a sudden on a slope of a hill, somewhere that is no significant, when we look in the stationary frame, we don't see any significant index profile. It's in fact, the index profile looks like that. It's a slope, right? Right in the middle of it, at some point, we trap the light, and we are able to guide it in this fashion. So that's the interesting part. We also, back then, we made a video, and it's just to show that this is such a simple concept and very repeatable experiment. So I'm going to play it. Let me see if I can make it even larger as well, even though I think you're good. Hello, my name is Mercedeh Khajavikhan, and this is the setup we built at USC to observe one first. I don't know if you hear it. I will hear it. Okay. So I basically say that this is the setup we built at USC to see the Lagrange points. These are Dimitri, the students. I put it on YouTube, so I had to give them the credit. All right, so this is the tube that I talked about. All right, so this is the tube, and we, of course, put the paper just so that, not to hide the rest of the lab, but just to, for you to be able to see the beam a little bit more clear. That's the wire that you see inside the tube, is the wire that I talked about. And there is a setup that we actually focus a laser beam from a helium neon laser to the entrance of the tube from the top, right? And then we are, in the experiment, the pictures that you saw was sometimes we take an image of the tube from the side, and sometimes we actually look at the output of what gets out of the tube, and look at the profile of the beam to see how much diffraction it goes through and how much the beam is expanding. All right, so what you see here is that we turn on the current, and we are, at this point, the current is turned on, and so there is a 4 amp of current is going through the wire, and basically that heats up the wire, and heating up the wire because the tube is at room temperature, there is a temperature gradient, and as I said, the temperature gradient, because your material has a negative thermo-optic coefficient, the index is highest on the walls of the tube. And this is also evident if you look at the beam that is actually, I don't know if you see it, but it deflects towards the wall of the tube. You see that? It's because the index is higher at the wall, and of course light goes wherever the index is the highest. Okay, so then, I mean, in the video I basically tell Yan Xuan to move the tube so that the beam will hit the Lagrange point. And that's what he does. So it's just that I say there's 4 amps of current and everything, but then at some point he should start to move the, I don't know what else I'm talking about, but possibly I say that this is PDMS, it has negative thermo-optic coefficient, the beam is coming from the top. Okay. Right, so basically what he does is he moves the tube so that the Gaussian beam that we have, the laser light, comes to the, and you can see that once he reaches the point, the beam is guided and nicely goes through, and you can see that it follows a helical path. Then, of course, because I'm sadistic, I say, move it out, move it back, and that's what you see. So everything is repeating, just to show that it is very easy to get to that point and get out. Okay? And somewhere, I mean, later on, so this is what you see. And then somewhere I said, if I turn off the heat, the current, so the heat goes away, then the beam, and that's what he does, turns off the current, and then you see that the beam starts to diffract. You see that at the end of the tube, the beam is diffracting. It's no longer, it takes a few seconds because it is a thermal effect. And then I would say, turn it on again. And that's what he does. And you can see that immediately, it forms the Lagrange waveguide and the light is guided. So it's a very repeatable experiment. I don't go through all the details of how we can actually change the parameters. A lot of people are asking me, is it possible to actually guide light? It's very big. Can we make it small? Yes, of course. We did it big just because it's much, much easier to make it this way and observe it. But we can go even to a micro level structures. They're asking me, do we need thermo-optic coefficient, or do we need the current and everything? Of course, again, you can even fabricate, if you can do a 3D index writing, you should be able to fabricate an index profile that give it to you. Other ways of generating it, I'm pretty sure there are. A lot of freedoms. You can get we use the negative index potential just because we wanted to show it very dramatically that we have, even in a defocusing medium, we would be able to actually guide light. But you don't necessarily need a defocusing medium. You can even use a focusing medium. So it's actually very, a lot of parameters in your hand to actually change and play with the thing. The next thing is I just want to show you that we actually measured the phase profile. And as we expected, this is the XY profile that you see here. And this is the lower side is when you have a Gaussian beam and you have no current passing through the wires, so the Gaussian beam just propagates. And you can see that that's the standard Gaussian phase profile that you expect. And the upper one is what we get from the Lagrange waveguide. This is from a double helix. So also you can see that even though light propagates along a straight line, you still get this phase profile. But as I said, it's an indication that things are rotating. So basically, the phase profile also follows that. Some of the possible routes that we have thought about and we would like to pursue is to actually get them to lasers. We would like to make cavities and make lasers out of them. We would like, because we know that the light propagates along a helical path. We know that we have higher degree of light-matter interactions in this system. And we can manage this to make this pitch very small, and that would make a substantial amount of light-matter interaction. This is a nice way of guiding light in liquid and gaseous media. And we would also like to study dispersion. This is a pretty broadband effect. And we would like was still to study the dispersion in these systems. But what we found as the, yes, go ahead. Whatever is in the waveguide, you go too far. It's a pretty, actually the mode, you can, as I said again, this is the fundamental mode. You can design it to be similar to with the fiber, that with the index contrast, you can actually make the guided mode, the fundamental mode to be larger, to be smaller. You have a lot of options here as well. So these waveguides that I showed, I mean the beam size that you get at the end, in this one, it's a multimodal structure. You get almost 50, 60 to 100 micron size of the beam. So, I mean, whatever molecules that are sitting there, and they contribute to the reaction. Especially if you're gaseous medium, I wouldn't go worried about that. All right. Actually, this is a good time to start the second part of the talk, which is now, it's interesting, but unfortunately, or fortunately, in fact, in optics, we have fibers, and fibers are extremely good medium for guiding light. And I don't foresee that anybody takes out the fiber optic links from under the ocean and puts a Trojan waveguide there. However, there are systems that, or there are environment that guiding is actually, for other wave particles, guiding is not as trivial as we get in optics. In fact, as I said, the really plus point of optics is the fact that we have guiding. Even in quantum optics, in quantum optics, we actually go from processing information in other medium, like with the ions, and then for transferring the information, we use light. So that's how good light is for transforming information. So we looked at this concept in the context of guiding electrons or other charged particles. And of course, you know, it's almost surprising that how little time has passed since we know that an electron exists. It was in 1897 that the electrons were discovered. And then I think proton was discovered in 1917 by Rutherford. And we have this all marvel of electronics industry that is enabled by these discoveries, and of course the works prior to them by Faraday and others. Nevertheless, to this day, we do not have a waveguide for electron beams. We have mechanisms to transfer electron beams from one location to another, but we do not have the concept of waveguide. It's like making continuous noise in my ear. I don't know why. But we don't have this concept of making waveguides for electron the way that we have waveguide for photons. And in fact, this concept of waveguides, we can actually, it's like we can send the information in a waveguide, in an optical waveguide, in a single mode that basically preserves the coherence of the information that we put on one side, right? It's actually the ground state of the system. So none of that exists in other modalities that we actually can use for charged particles like electrons to guide them. And so the trapping of the charged particles is mostly done through these Paul traps and Penning traps. And I think Paul was German, right? At least, okay. Yes. And there is Wolfgang Paul and Wolfgang Pauli, I'm guessing everybody. And he used to say that he's the imaginary part and I'm the real part. But so the Paul trap is actually what I told you about. So the Paul traps work based on this principle of a strong focusing. And what they do is basically they have these quadrupole magnets. And so we have the plus and plus in the, or, you know, north and north in this side and south on the other side. And then in order to actually, so as you can see, these points, these magnets are actually generating a saddle point. So they trap in one side and actually untrap or on the other side. So then they use a RF signal to actually signal to change this. So very quickly they change, it becomes minus, minus, maybe it's the other side, yeah, minus, minus, hopefully it is, plus, plus, and that would basically change it. And that's how they are in time, they trap the particle on that location. So they use time and some sort of, again, dynamical stability in order to stably keep the point over there. And this is the picture of basically, this is, as I said, it's a saddle point. So it sits there, but it can actually anytime, in one direction, it is trapping, and the other direction is actually anti-trapping. And in the CERN and other these super colliders, so what they do is to use again these quadratic lenses, magnetic lenses, where they have these very nice lenses, which you can see that they are. I think there are some statistics written, not statistics, some data is here. So in a 27-kilometer accelerometer that in CERN, there are 392 quadrupole magnets. Each of them is 5 to 7 meters. There are, of course, everything, because we are guiding electrons in vacuum at the end of the day. They're all, the entire system is under vacuum. I just recently learned that the vacuum is as much as the vacuum that we get on Moon. So maybe we should do these experiments there, if we can get there again. All right, and my eyes don't see properly, but they're all kept at cryogenic temperatures. They are superconducting coils, and so on and so forth. So as you can see, nothing is trivial there. Actually, in order to make this guiding, you have to use this quite expensive. And I remember at some point, I checked the prices. They are almost cost each of them $1 million. So this is $500 million sitting there, just with the magnets. So it is so important that we actually come up with a way to guide light. And as I said, the way that they work, they are lenses. They are not really waveguides. So they focus the electron beam, and then, or mostly in these cases, the ion or proton beams. And then they defocus, and then they put another lens to focus it and defocus. So it's basically the principle of operation is focusing, defocusing, and that's how these charged particle beams are actually transferred from one location to another. So again, the idea is, of course, if we can use these Trojan waveguides or Lagrange waveguides, whatever you like to call them, for guiding these charged particles. And of course, if we saw already the paraxial wave equation is similar to Schrödinger equation, and we just talked about it at the beginning of the talk. And you can see that once you are in a rotating frame and you generate this potential. Now this time, of course, we are talking about electromagnetic potential or electric potential. So you actually would be able to get the trapping of the beam. In this case, electron beam. So the setup that we came up with is this setup. We are actually using an electron gun to generate the electrons. It's, I think, a 30 kilovolt, and it's actually built by a company in Germany. And we have this assembly to actually send this beam of electrons into the waveguide. Now, our waveguide is different from the one that we have in optics, even though it has similarities. It is different in the sense that instead of using temperature distribution, because we needed their refractive index profile, here we need the potential. So we are actually using a wire kept an electrostatic potential of V naught, and we can do the calculations. You can see that it actually traps the electron beams and guide them through this Lagrange kind of helical path. And these are simulations. You can see the probability amplitude of the electrons. You can also see the trajectory, which is fairly similar as you can guess from because the similar equations are governing them. They're fairly similar equations in form and in result. So these are two sets of parameters. For example, you can see that if you have a if your electron beam has a 30 kilo electron volt, and your voltage that you're applying to your wire, electrostatic voltage, is 35 kilovolt, you get, and with this the pitch of 0.2 millimeter, you would be able to get a spot size for the electron beam that is 40 nanometer. If you are, of course, going to smaller voltages and larger pitches, you would get the size of the ground state, or the fundamental mode is going to be larger, in this case 0.6 micrometer. So as I said, there are lots of parameters in your hand to actually change and study the system. This is the experimental apparatus. It's almost built, and we are hoping to be able to do the experiment in the next perhaps month or so. And as I said, this basically starts with the electron gun, and this is where the, cannot really see, but I'm guessing that's the place. This is where the helical wire is kept, and there are a lot of details which I don't bother you, especially if you're not in the field of electron beams. It's not necessary. It's another view of the system. Another thing that we actually discovered about when we were looking at the charged particles was this kind of a peculiar effect. So we know that these waveguides, depending on this, parameters that we put, they can also become like a fiber and other waveguides. They can become multimodal. However, when we actually look at and remember that we had the potential that looked almost like a parabolic kind of a potential, inverse parabola. So when we look at the states of this system, the modes, we actually see that in a very counterintuitive effect, we get two ladders. So we get a set of modes that actually, if this is our ground state, a set of modes that follow this ladder, right? It goes in this way. And there is another ladder up there, which actually, again, you see higher order modes on that side. So these are the images of the the pictures of the various modes. The first one on the top is the fundamental mode. Now in one direction, ladder 1, the first mode is like that. In the ladder 2, the first mode looks like this. It's like one of them is vertical, the other one is horizontal. And this comes from the fact that, and they are not exactly similar. It comes from the fact that, remember when I showed you the picture where the Sisyphean force was there, you could see the potential. And the potential, because we are in this helical trajectory, the potential is actually, it looked like this, right? Remember, it was the opposite of the trapping. And in one, it's not exactly the same parabola in the two direction of u and v, and that's what you're basically seeing the result. There are two parabola, and these two parabola in the x and y are actually having different parameters, and that's what you get. This is a picture of this is basically the result of the histogram that shows of the electron trajectories. If there is no voltage applied to the helical wire, you would not get, the electrons will just scatter, and they come out and they have a histogram that follows this. And once you apply the voltage, they would come in a mode, and they are very confined, and they do not scatter. It's also actually interesting to look at the trajectory within a cross section. And as I said, this is like when you consider them as particles, it's as if the particle, the electron, is basically, it's exactly like what happens in a celestial mechanics, where you put that object, the asteroid, and it is a dynamical stability, and the Coriolis force as the system rotates brings back the system to the original location. This is the same thing. As you can see, the electron follows this path in the cross section, follows this path. So basically, it is not one point that it stays. It tries to escape, and it is returning back to the original position. We also looked at the loss that this waveguide has. So, and this is possibly one of the most important results of this work. In fact, in the case where we have a helical path, when the electron travels or charged particle travels along a helical path, it starts to actually radiate. And this synchrotron radiation, we can actually calculate it. The value that we did this analysis already in the non-relativistic case and also the relativistic case. In the case of this, I think the one that is here is for the non-relativistic case where we have 30 electron volt. And you can see that the loss is in the order of 410 to the power of minus 10 dB per kilometer. And this is extremely low. I mean, it is, for the fiber, we have 0.2 dB per kilometer. This is the loss that we have. Remember, we are actually transferring electrons in vacuum. So it's not that we have any material loss or any hidden losses that we are not really putting it there. The loss is this much. The waveguide can afford some level of, I think when we did the calculation, it's about 6 degrees of, angle. We can have a rotation, tilt or, change of the path. Nevertheless, the loss is extremely low. And even though it is loss, we have to remember that this is energy loss. So I think at some point it's written 0.27 dB electron volt per second. So it's an energy loss. So we are, unlike photons, that once we actually have loss, it means that we are losing photon, it's gone, we are never gonna get it back. In this case, the loss basically just means that the energy of the electron that used to be whatever, for example, in this case, 30 electron volt, has dropped by a factor by this much of the value, so 0.27. So we are not losing the electron. We just, its energy is actually decreasing. So a lot of, you may think that if you are doing some quantum experiments, you would be able to actually save this information. We can also use this, we can actually send the electron. For example, this is an idea for a mass spectroscopy. You can send various particles, and you expect that this waveguide will happen different locations for them, and you would be able to actually separate these different particles from each other. That's one application. There are another thing that we have thought about is to actually so the idea is to bring all the nice things that we can do to optics to electron beams. And one of the most enabling things in optics is this idea of a beam splitter. Once we have a beam splitter, we can actually start to make an interferometer. We can do a lot of other things. So the idea is now, can we actually do similar things in Lagrange waveguides with the electron beams? And the answer is, of course, yes. We can actually design structures that will support 2 Lagrange points, and if we manage to get them fairly close to each other, the wave function of these 2 electrons, for example, beams, start to actually overlap, and you would be able to get these ideas. We can think about a lot of applications based on these systems. We have for particle acceleration, for dispersion transportation of the electron beams, X-ray free electron lasers. We thought about using it for, in fact, there is some discussions with the Duke University where they have these ion traps quantum systems for quantum computing, and we want to actually be using these structures, these waveguides for guiding ion beams from one location to another. At the end of the day, we think that this would be a very enabling technology for lithography, for high-power microwave generation, material characterization, electron interferometry, and sensing. And these are some of the future works that we have envisioned. Of course, we better first get the experiment done and show that this is in fact working. And then we would like to study some theoretical studies to identify practical limits in E-beam waveguides. What basically limits the size of the beam, how many amps of current we can actually pass through them, what are the losses. We would like to study them under relativistic conditions, because most of these accelerators are actually in fact deal with relativistic charged particles. Guiding, we would like to study guiding protons and low velocity ions using similar approaches. We would like to make cavities out of them for electrons, and this may have some applications for quantum computing. And we are still in the very early stage of the work where we don't know what possibilities are coming around. So we are basically trying to just understand the merit of this approach for anything useful. And with that, let me thank you for your time.
Yeah, thank you very much for the great talk, which was very inspiring, and I think there must be questions, so anyone.
So what is the longest that you have built these guides for light? So these PDMS with lines, what's the longest that you've built that?
I would say we only made one size, 30 centimeter. Okay.
But what do you think, how long can you make it in your lab? Like here, how long did you make them?
This is a very good question. In our labs, I mean, the largest tube that we can find, I mean, if you with this approach, right? I don't know. I mean, I was never interested to do that. I don't know. I mean, as much as the need is there.
I think Gerd was next.
Yeah, thank you very much. When you started out, I think I never really thought about the Lagrange points in celestial mechanics. I knew about them, but I don't think I ever thought in any depth about this. And I thought, oh, this is like in Paul Trap, but then you mentioned it.
But it is not. They're different, but yeah, I mean, in
but
some
the
L1,
L2 and L3, they're similar,
Yeah,
because they are subtle. So this is
and
similar.
what they do there, they actually in the Paul trap, they change the voltage, you know, the RF, to change the location of the two to basically trap it.
But here you also change
Yeah, we
because
are
of
also
the rotation.
Yeah.
So
In some ways, yeah.
it's not exactly the same. Actually, one time when Wolfgang Paul was very old, he came to a conference and gave an evening talk about his life. So he was so old that he was allowed to sit and didn't have to stand while he talked. That was very interesting. Now, I was wondering, at some point you said when people transport electrons, charged particles, this is all very expensive and has to be in vacuum. But Lagrange point trapping eventually also will have to be in vacuum.
Yes.
I think
Vacuum
there's
has to be vacuum.
no way to get around vacuum, right?
Because as soon as you have material, the electron hits the material,
scatters,
scatters, like
yeah.
what happens in semiconductor. The highest speed you can go is about 10 to the power of 7 or so.
I think Masha was next.
Thank you very much. Again, can you trap atoms like that? Atoms in light beams somehow?
There has to be some charge because we are using the potential, right? I mean, so the atoms, I wouldn't say that it works.
Dipole force.
Yeah, maybe with that, yeah.
Next.
Very intriguing. Thank you so much for the nice talk. So I like this analogy and how you came about it with the celestial mechanics Lagrange point, right? So the James Webb is actually orbiting the Lagrange point at a halo orbit, right? So I wonder if that basically...
I mean, you said that...
The James Webb telescope, which is at the Earth-Sun L2 point, it's not at the Lagrange point, but it's orbiting on a halo orbit around the L2.
Because they have to keep it there, right? I mean, it is at the L2.
Yeah, no, it's not exactly at L2. It's orbiting around L2 because
But
that's
they
the
use
most
the
efficient,
thrusters.
the most stable location that you can get in. So I wonder if basically here in your system, if you would go to the reference system, to the rotating reference system, if actually the light path or the most stable light path would be also a halo orbit around this, equivalent to the Lagrange point. Does that make sense?
Yeah, I mean, I don't know if you saw when I showed the trajectory of electrons, we would be actually, in fact, also the trajectory of if we use the ray optics, also the trajectory of the ray, as well as the trajectory of if you look at it in plane, right? I mean, so that means that at one given time, yeah, you look at it, it looks as if it is actually it's let me just you see it goes around. It's a dynamical stability. So I don't know if that's
Yes,
what
exactly. And so if you would go to the rotating frame in time,
Yeah.
if that actually would be equivalent to a halo orbit in
Yeah.
celestial mechanics, because that would kind of make sense, right? If that's
Yeah, I mean, so it looks like that. Yeah.
Thanks.
So I think I saw someone.
And I wonder if you choose the point wavelength for light. Will the language point be disturbed, or is more robust to different wavelengths?
Can you repeat it again?
Yeah, I wonder for your case, if you change the wavelength of the pump light, will the Lagrange point be
Yes,
disturbed?
it
or not?
would change it slightly. I mean, of course it does, yeah.
Maybe Olga.
Thank you for a nice talk. So if I'm getting right, from your calculation at 35 kV, you will get a spot for e-beam around 40 nanometers.
Yeah.
Did you make a calculation for the stall or limitation of the spot size? Because if it will work like you were mentioning, it will be a really new step in maybe designing of e-beam lithography, and where is the limitation of your
did,
imagination?
Yes. Yeah, no, we did. I was hoping that this would be different numbers here, but we did it. For example, if you use higher applied voltage, you would be able to get it smaller. We know that you can go to angstrom level. We can. Of course, the values are very high, like in 1,000 kilovolt or megavolt, which is very difficult to get in the experimental setup, but it's possible.
And the second question, so you're now designing a setup, probably with 30 or 35 kV, I guess.
Yes.
So calculation, it should be also possible to easy to calculate if you're applying higher voltage, like using different source for beams, like will you get a like Armstrong level?
With the system that we have with the electron gun that we are using, which is a 35 kilovolt, I don't think so.
The limitation will be Armstrong spot size. Yeah.
I think even it goes below angstrom. I think it is 10 to power minus 11. But yeah, I mean, in principle, you can get there. It's just that it becomes tougher and tougher to get it. You have to understand, like optics, the experiment that we did in optics, by no means we are trying to optimize anything in particular. We just want to show the proof of concept and the path to get there. It's especially without, I'm not really an electron system person, so it's my very first experiment in this area, and that's why I work with another company to do it. It is, we targeted the easiest experiment that we can show the concept. So what we have is the electron gun, we have the waveguide, of course there's some assembly to actually, shape the beam and send it to the right place and change the location, because we have to search to hit the right point, which is the Lagrange point. And of course, as you go to smaller and smaller waveguide spot sizes, you're also going to limit the number of electrons that you can get in. And then at the end, we have the phosphorus monitor to just look at the diffraction of the beam. And our goal is to just at this point to show that guiding is happening. Once we establish that, we can now go for next system.
Nice.
Yeah, very good. So maybe one last question.
Yeah. So I understood that the waveguide that you introduced has a different phase distribution compared to Gaussian.
Yes.
How do you couple light to this waveguide? Do you use collimated beam or still focus beam?
We focus the beam to the entrance of the waveguide. But, well, if you are really, if you really want to match the phase, all you need to do is to actually put a phase plate that does the job. So
you have a low coupling efficiency, right?
I'm not sure why you think that way. Why is that? Why do you think that it's a low coupling efficiency?
The phase is not matching.
When it comes to a waveguide and coupling light to it, you have to consider, you know, the numerical aperture, things of that sort. As I said, the phase, you can always correct it if that's what you want.
Okay, is there any last? Any cat?
So one thing I have not. So I can see if you have the saddle point and it's rotating, it's trapped. This seems to be straightforward. Now, when you have this maximum, of course, in the celestial, it's kind of rotating, but it seems less intuitive. So, what is the picture that you use that you're most happy with to understand for yourself that this is trapping?
I use this Coriolis force that I feel that it's trying to escape and it return, you know, when it's like a Coriolis force that remember the force that they draw it this way, so it brings it back. This is the most intuitive way for me.
Coriolis force, of course, is not a real force, it's only
the force
but
that you understand it only in the co-rotating frame.
Yeah,
The other
right,
thing
exactly.
is, actually, perhaps the easiest way is to look at this one. When we did the simulation, so this is what the index profile in the XY plane, right? When you are in a stationary frame. Now, if you look at it, the same thing in the co-rotating frame. Look at it; it actually is like that. So it's trapping.
Okay, I think in the interest of time, we stop at this point and thank the speaker again for